This lesson will discuss stoichiometry. First, let's make sure we understand what it is. It is, after all, the most important concept in chemistry. To define stoichiometry, we would say it is the ability to determine the quantities of one or more substances in a balanced chemical equation when the quantity of just one substance in that equation is known. Stoichiometry requires a balanced chemical equation because a balanced equation shows the relationships between the different substances involved in the reaction. The stoichiometric coefficients, the large numbers to the left of each substance in an equation, show the ratio between the substances in a reaction. This example, which reads 4FeS2 plus 11O2, produces 2Fe2O3 plus 8SO2. In this reaction, the equation is expressing that for every 4 molecules of FeS2 and 11 molecules of O2 that react together, 2 molecules of Fe2O3 and 8 molecules of SO2 are produced. Now, since we can't actually count individual molecules out by hand, we use these same ratios and talk about reactions involving large groups of these molecules at a time. Just like a dozen is a group of 12, there's a group called a mole, which is 6.022 times 10 to the 23rd things. Here is that number written out with all of its zeros. So instead, we can say that this equation is expressing that for every 4 moles of FeS2 and 11 moles of oxygen that react together, 2 moles of Fe2O3 and 8 moles of SO2 are produced. Moles, however, cannot be easily measured out for use in reactions. Instead, substances are measured out in grams, using mass scales. This requires that we have a way to convert between grams and moles as necessary. The gram is too large of a mass unit for a single atom or molecule. When the mass of a single atom or molecule is calculated using the periodic table, the mass unit being used is the atomic mass unit, abbreviated AMU. If that unit is changed from AMU to grams, the value now represents the mass of 6.022 times 10 to the 23rd of the atoms or molecules. Let's look at an example and use our periodic table to find the mass of a single molecule of calcium carbonate. That mass can be calculated using our periodic table. We find the mass of a single calcium atom plus the mass of a single carbon atom plus the mass of 3 oxygen atoms for a total for that molecule of 100.09 atomic mass units. If we change the units to grams, we have 100.09 grams. That is the mass of 6.022 times 10 to the 23rd calcium carbonate molecules, or 1 mole of calcium carbonate molecules. This gives us the gram-mole relationship. 1 mole calcium carbonate equals 100.09 grams. That relationship, because of the equal sign, can now be written as a form of 1 fraction, with either item on the top or bottom, allowing us to cancel units as necessary in calculations. Now it's time to apply these concepts to a stoichiometry problem. Given the following reaction, which you see in front of you, if 200 grams of potassium permanganate, that would be the first reactant that you see, are completely reacted, what mass of water would be produced? Water is the last product in this equation. Information is being provided about one substance in a reaction, the first reactant, potassium permanganate, while we are asked to find information about another substance in that same reaction, that last product, water. This identifies the problem as stoichiometry. Once you've identified a problem as stoichiometry, the first question to ask is, do we have a balanced chemical equation? In this case, we do. If we didn't, that would be the first step we would need to take. Second question, how do we get from the provided information, grams of potassium permanganate, to the requested information, grams of water? Well, it would be very nice if we could go directly from grams of potassium permanganate to grams of water and make that conversion, but there is no direct relationship. Instead, we need to find moles of potassium permanganate, then moles of water, then grams of water. Each arrow that you see in the diagram represents two actions that need to be taken. Find a relationship and use that relationship in a conversion. Let's see how that works. First, we need to find a gram to mole relationship for potassium permanganate. So pulling out the periodic table, we find the mass of one molecule of potassium permanganate. Looking up again the masses of each element contained in that compound. That's a total of 159.04 atomic mass units. And we now know that that means 1 mole of potassium permanganate weighs 159.04 grams. Now we can use that relationship in a conversion. We take our given 200 grams of potassium permanganate, multiply it times our form of one fraction from the relationship. We're putting grams on the bottom this time because we need them to cancel using our rules from algebra for multiplying fractions, and we want to end up with moles, which is why it's on the top of the fraction. We end up with a value of 1.266 moles of potassium permanganate using the significant figure rules that you would have learned at the beginning of your textbook. And we will just record our progress in the bottom right side of the screen there. Now we have gotten to moles of potassium permanganate. We need to follow the diagram over, meaning we need to find a mole-to-mole relationship for potassium permanganate and water. So we look up at our balanced chemical equation. We see we have 2 moles of potassium permanganate for every 8 moles of water. Now we can use that relationship in a conversion. The last step we calculated that we had 1.266 moles of potassium permanganate. We multiply that times our relationship, putting our moles of potassium permanganate on the bottom of that fraction so they will cancel and leave us with moles of water. We find out that we have 5.064 moles of water. And now we need to find the mole-gram relationship for water. Again, using our periodic table, we find the mass of one water molecule, adding together the masses of the 2 hydrogens and an oxygen. And we find out that 1 mole of water weighs 18.02 grams. We use that relationship in a conversion, using our calculation from the last step, 5.064 moles of water times 18.02 grams divided by 1 mole. Again, moles on the bottom, so it will cancel, leaving us with grams of water, which is what we were originally looking for. So we have found that we have 91.25 grams of water. That is our answer. I hope this has helped you to understand the concept of stoichiometry. If not, feel free to send a question.